Hello everyone. So, today we will consider thermal boundary layer over a flat plate and we will find the temperature distribution using similarity method, and this solution is known as Paul-Heysen solution. We will consider two dimensional steady laminar flow with constant properties. The free stream temperature T infinity is constant and the wall temperature T W in general we will consider that it varies with x, which is the axial direction. Later we will consider a special case where we will assume T W as constant. In last class we have already solved the velocity distribution using similarity method. As we are assuming that properties are constant, so velocity distribution is independent of temperature distribution. Here we are considering low speed flow, which is incompressible flow. So, we can neglect viscous dissipation effect. First, let us write down the energy equation and let us introduce non-dimensional temperature theta, which is T minus T W divided by T infinity minus T W. So, energy equation for steady laminar flow, we can write U del T by del x plus V del T by del y is equal to alpha, which is your thermal diffusivity, into del 2 T by del y square. So, this is the thermal boundary layer equation, right. So, we are neglecting the viscous dissipation effect, and now let us introduce non-dimensional temperature, theta as T minus T W divided by T infinity minus T W. So, here T infinity is the free stream velocity and that is constant, but T W, which is your wall temperature, in general we will consider T W as function of x, okay. And as a special case later we will consider that T W is constant. And you can see if T W is greater than T infinity, so temperature distribution will look like this, because at the wall we have maximum temperature and free stream temperature as y tends to infinity. So, with this, now if I write the energy equation, then we can write U del theta by del x plus V del theta by del y is equal to alpha del 2 theta by del y square. So, now let us write the boundary conditions. You can see at the wall where y is equal to 0, you have T is equal to T W, and y tends to infinity, means away from the boundary you have free stream temperature T infinity. You can see that as x tends to 0, at the leading edge of the flat plate we have free stream temperature T infinity. So, at y is equal to 0, you have T is equal to T W. So, theta will be 0 at or y tends to infinity. So, obviously it is away from the wall. You can see at the edge of the boundary layer you have T infinity. So, T is equal to T infinity, and you can write theta is equal to 1, and at x tends to 0 you have T is equal to T infinity. So, theta will be 1. Now, we have already solved the velocity distribution using similarity method. Can we have some similarity with the momentum equation and the energy equation when nu is equal to alpha? Okay, so, when will be the nu is equal to alpha? When Prandtl number is equal to 1. So, as a special case, let us say for Prandtl number 1, Okay. Your nu you can write is equal to alpha, okay. And the momentum equation whatever we have, so you can write down u del u by del x plus v del u by del y is equal to nu del to u by del y square, and this u, okay, you write in terms of non-dimensional velocity, u star is equal to u by u infinity. Then you can see, you can write u del u star by del x plus v del u star by del y is equal to nu del to u star by del y square. And what are the boundary conditions for this equation? At y is equal to 0, okay, u star is equal to 0, no slip boundary condition. At y tends to infinity, you have u star is equal to 1, and at x tends to 0, you have u star is equal to 1. Now, you see these equations. This is the energy equation where theta is the non-dimensional temperature with these boundary conditions, and this is the momentum equation where u star is the non-dimensional velocity and these are the boundary conditions. So, if you compare these two for Prandtl number 1, so these are the same equation, because if you replace theta is equal to u star, then you can see the boundary conditions are same and nu is equal to alpha. So, both equations are same. So, you can write for Prandtl number 1, theta can be replaced with u star, that means you can write theta is equal to u star, that means T minus T w divided by T infinity minus T w is equal to u by u infinity. So, you can see already we have solved the velocity distribution using similarity method, and we could convert the partial differential equation to ordinary differential equation using similarity approach. In this case, whatever we have shown now, that for Prandtl number 1 as a special case, the governing equations, energy equation as well as the momentum equation are same and theta is equal to u star. So, obviously, we can have the similarity solution at least for Prandtl number equal to 1 for the temperature distribution. So, we will use the similarity method to solve this energy equation and we will find the temperature distribution, and if we can convert for other Prandtl number, for Prandtl number not equal to 1, this partial differential equation to ordinary differential equation, that means similarity solution exists for Prandtl number not equal to 1. So, you can see that the temperature distribution at any location, say let us say x 2, and another location if you see here. So, it will have free stream temperature T infinity and you have let us say T w. So, this is your T infinity, this is your T w and this is location x 1. So, you can see that the temperature distribution if you see here and here for let us say T w is equal to constant, you can see that these are similar profile. So, if you can scale down the temperature distribution at location x 2 with a scaling factor, then you can get the same temperature distribution at x 1. So, that means, so whatever temperature distribution say we are getting here theta versus y at different x location. Okay. So, this will be, you can see that at y is equal to 0 you have theta is equal to 0 and y tends to infinity, it will be 1. So, you will have another profile, you have another profile. So, you can see these are the temperature profile at different x locations. Now, if you use this similarity variable, then you can see that if you plot theta versus eta, then it will all the temperature profile will fall in same curve. Okay. So, it will fall in same curve. So, let us start with whatever similarity variable eta we have derived in earlier class, and we will assume that theta is function of eta only, because here you can see it might fall in the same profile. And using similarity method, if we can convert this partial differential equation to ordinary differential equation, that means your similarity solution exists. If you see the energy equation, in the energy equation u and v are known from the solution of velocity distribution. That means this is linear equation, because velocity profiles are known, only you need to find the temperature distribution. So, let us assume that theta is function of eta only, and eta already we have found in last class as y into u infinity by nu x. Okay. So, this is the similarity variable. Okay. So, we have written in terms of two independent variables x and y, and properties nu is constant and u infinity is the free stream velocity, that is also constant. Also, let us assume in general that T w is function of x. Okay. So, theta whatever we have written, so T minus T w, which is function of x divided by T infinity minus T w, and now T you can write as T w plus T infinity minus T w into theta. Okay. So, let us write the energy equation, okay, the derivatives in terms of this with respect to the derivative with respect to eta. So, eta we have y into u infinity by nu x. Okay. So, del eta by del y will be your root u infinity by nu x, and del eta by del x will be, you can see it is x to the power minus half. So, it will be minus half, okay, and it will be, you can rearrange it y by x u infinity by nu x, and this quantity y into u infinity root u infinity by nu x you can write as eta. So, you can write minus eta by 2 x. Now, let us find the derivative of temperature. So, we have del T by del x. Okay. So, it will be, so T we have written as T w, which is function of x plus T infinity minus T w into theta. So, del T by del x you can see. So, this will be total derivative, that means dt w by dx, okay, plus, so T infinity. So, this is constant, so it will be 0. So, minus, so it will be dt w by dx into theta, and you will also get plus T infinity minus T w into del theta by del x. Okay. So, now del T by del x you can write as, so you can see this, you can write 1 minus theta into dt w by dx, and del theta by del x now we can write as T infinity minus T w del d theta by d eta and del eta by del x. Okay. So, now del T by del x you can write 1 minus theta, we will write T w prime, which is your first derivative of T w, plus T infinity minus T w. So, this is your theta prime, and del eta by del x you can see it is minus eta by 2 x. Now, similarly you find the derivative of t with respect to y. So, del t by del y you can write, now you see t w is function of x. So, its derivative with respect to y will be 0. So, you will get t infinity minus t w, here t w is function of x, that I am not writing, and del theta by del y. Okay. So, you can write t infinity minus t w d theta by d eta into del eta by del y. Okay. So, you can see you can write t infinity minus t w theta prime and del eta by del y is root u infinity by nu x, and del 2 t by del y square. Okay. So, you can see it will be just t infinity minus t w theta double prime and another root u infinity by nu x will be there because del eta by del y. So, it will be u infinity by nu x. Now, we have also velocities u and v. So, that let us find. So, u, obviously you know that u is your u infinity into f prime, okay. And in last class we have already derived the velocity v in terms of capital F. First let us write that and then we will write in terms of f. So, v, if you see in last class we have written mu g f double prime by f prime minus u infinity y f g prime by g, okay. And if after separation of variables, if you see that we have written f double prime by f prime is equal to minus f by 2, okay. Eta already you know, so that we have written y into g. So, here y we can write eta by g, and g we have written u infinity by nu x, okay. And g prime by g cube, if you see the equation where we have separated the variables, that we have written as minus half nu by u infinity, okay. So, from here we can write g prime by g square is equal to minus half nu u infinity g, okay. And f, obviously you can see f is your f prime, okay, because that is your u by u infinity. So, now if you substitute all these here, you will get velocity v. So, it will be nu g. So, f double prime by f prime, it is minus f by 2 minus u infinity. So, y we can write eta by g, right. So, eta f is f prime and g prime by g square, okay. And g prime by g square we can write this one. So, you can write nu g f by 2 minus u infinity eta f prime. So, it will be minus half nu by u infinity into g. So, if you take half nu g outside and this minus minus plus. So, it will be eta f prime and the first term you can see it will be minus f, okay. So, it will be, and what is g? G is nothing but a half nu, g is your root u infinity by nu x, okay, eta into f prime minus f. So, this nu if you take inside the root, then you will get half u infinity nu by x eta f prime minus f. So, let us put all these values in the energy equation. So, energy equation is u del t by del x plus v del t by del y is equal to alpha del 2 t by del y square, okay. So, now one by one let us put. So, you have u is nothing but u infinity f prime del t by del x 1 minus theta t w prime, and another term will be there. So, you can see this term we have written and this term you can write now. So, it will be minus u infinity f prime t infinity minus t w theta prime eta by 2 x. Okay. Now, we have v into del t by del y. So, if you write it half u infinity by x eta f prime t infinity minus t w theta prime minus half u infinity by x t infinity minus t w f theta prime is equal to alpha into t infinity minus t w u infinity by nu x theta double prime. Okay. So, now you rearrange this equation. So, if you rearrange, you will get, so first multiply both side by x by u infinity into t infinity minus t w. Okay. So, you can see in the first term. So, u infinity will get cancelled. So, you can write x f prime 1 minus theta t w prime divided by t infinity minus t w. The next term you can see u infinity will get cancelled, t infinity minus t w also will get cancelled, and this x x. So, you will get finally eta by 2 f prime theta prime. Then here also u infinity by x t infinity minus t w is there. So, you will get eta by 2 f prime theta prime. Then the next term you can see here you will get only minus half f theta prime, and here you can see alpha by nu. Okay, that means it is 1 by Prandtl number, because Prandtl number is nu by alpha, right. Prandtl number is nu by alpha. Okay. Momentum diffusivity to thermal diffusivity. So, you can write 1 by Prandtl number and theta double prime. So, here you can see this is t infinity minus t w, it is 1 minus theta. We will write here x f prime theta minus 1 t w prime divided by t w minus t infinity, and you have minus, we will take in right hand side. So, it will be half f theta prime plus 1 by Prandtl number theta double prime. Now, divide both side by f prime theta minus 1. Okay. So, if you rearrange it, you will get x t w prime divided by t w minus t infinity is equal to half f by f prime theta prime by theta minus 1 plus 1 by Prandtl number 1 by f prime theta double prime by theta minus 1. So, you see we have separated the variables. If you see the left hand side, okay, it is function of x only, and right hand side it is function of eta only, because f is function of eta and theta is also function of eta. So, we have separated the variables. So, you can see this is t w. So, t w is function of x only. So, all these terms are function of x. So, this is function of x, and this right hand side terms are function of eta only. Okay. So, as left hand side equal to right hand side and left hand side is function of x and right hand side function of eta. So, it will be equal to some constant, okay, and that constant let us say that it is lambda. So, this will be equal to lambda. Okay. We have separated the variables. So, you can write it as x t w prime divided by t w minus t infinity is equal to lambda. So, you can write dt w. So, t w prime means dtw by dx. Okay. So, we will write dtw by tw minus T infinity is equal to lambda dx by x. So, now integrate. So, you will get ln tw minus T infinity, okay, into lambda ln x plus integration constant ln c. So, you can write tw minus T infinity is equal to c x to the power lambda, or tw is equal to T infinity plus c x to the power lambda. We have assumed that wall temperature Tw is function of x and it varies in this way. Okay. As a special case, you can see that if lambda is equal to 0, okay, if lambda is equal to 0, then you will get Tw is equal to T infinity plus some constant c. So, T infinity is constant and c is constant. So, this is equal to constant. So, you can see that it is a case of uniform wall temperature. So, this is a special case, okay, but in general we have derived, and Tw varies as T infinity plus c x to the power lambda. Okay. So, now let us consider the other terms, okay, which is function of eta only. So, if you consider that term, then you will get half f by f prime theta prime by theta minus 1 plus 1 by Prandtl number 1 by f prime theta double prime by theta minus 1 is equal to lambda. Now, multiply both sides by Prandtl number f prime theta minus 1. So, what you will get? You will get half Prandtl number f theta prime plus theta double prime is equal to lambda into Prandtl number f prime theta minus 1. So, you will get theta double prime plus Prandtl number by 2 f theta prime minus lambda Prandtl number f prime theta minus 1 is equal to 0. So, you see that this equation is ordinary differential equation. So, we started with the partial differential equation and we used similarity transformation and transferred this partial differential equation to ordinary differential equation for Prandtl number not equal to 1 as well, because it is function of Prandtl number. So, that means similarity solutions for this temperature distribution exist, and we could get this second order linear ordinary differential equation. You can see this is second order, and as f is known, f and f prime are known from the velocity distribution. So, obviously this is linear equation. So, you can see this is second order linear ordinary differential equation okay, and this equation is known as Paul-Heysen equation. Okay. And you can see as a special case for uniform wall temperature you can put lambda is equal to 0. So, for lambda is equal to 0, which is a special case, okay, Tw is constant. For that you can write the Paul-Heysen equation as theta double prime plus Prandtl number by 2 f theta prime is equal to 0. Okay. So, you can see here this is your linear equation because f is known from the velocity distribution, and this is the second order linear ordinary differential equation. So, this equation now you can solve using some numerical technique, okay, and find the temperature distribution, and once you get the temperature distribution you will be able to calculate the heat flux, and from there you can calculate the heat transfer coefficient and Nusselt number. Now, let us consider the special case when the flat plate is maintained at constant uniform temperature. So, that means T W is constant, and whatever Paulian equation we got, now let us find the solution of this ordinary differential equation applying the boundary conditions. So, for lambda is equal to 0, okay. Here now T W is constant, we can write theta double prime plus Prandtl number by 2 f theta prime is equal to 0, okay, where T W is constant. Okay. So, this is a special case for lambda is equal to 0. Now, what are the boundary conditions? At eta is equal to 0, okay, because y is equal to 0, you will get eta is equal to 0 and it is your T W. So, that means T W minus T W will become 0. So, that means theta will be 0, and at eta tends to infinity, okay, when y tends to infinity and x tends to 0, these two boundary conditions, okay, are merged into one, and for eta tends to infinity you can write theta is equal to 1. So, now you can integrate this equation. So, you can write theta double prime by theta prime is equal to minus half Prandtl number into f. So, what is theta double prime? You can write d of d eta, right, d of d eta of theta prime divided by theta prime is equal to minus half Prandtl number into f. So, integrating the above equation, so what you will get? So, d theta prime divided by theta prime is equal to minus Prandtl number by 2 f d eta, okay, and you integrate it 0 to eta. Okay. So, if you integrate, what you will get here? ln theta prime, which is function of eta, I am not writing that, and theta prime 0. Okay. So, at eta is equal to 0. So, this is having some constant value, right, theta prime 0, because at eta is equal to 0 you are finding the temperature gradient is equal to minus 0 to eta Prandtl number by 2 f d eta. So, unless you know the velocity distribution f, f primes and f is the stream function equivalent to stream function, you will not be able to integrate. So, we are keeping it in terms of integral form. So, if you write this, so you can write d theta by d eta is equal to, so in right hand side it will become exponential. So, it will be theta prime 0 e to the power minus 0 to eta Prandtl number by 2 f d eta. Okay. So, integrate this above equation, integrate the above equation. Okay. So, we will integrate integral d theta is equal to theta prime 0 is constant, right, means at eta is equal to 0 you are finding the theta prime, and integral e to the power minus 0 to eta Prandtl number by 2 f d eta into d eta. Okay. Here we will put the limit from eta to infinity, okay, eta to infinity. Okay. So, if you put it, then what you will get? Theta at eta is equal to infinity minus theta at eta is equal to theta prime 0, and this is your eta to infinity e to the power minus 0 to eta Prandtl number by 2 f d eta d eta. Okay. So, now you see theta at eta tends to infinity, we have the boundary condition theta is equal to 1. So, you can put this is as 1. Okay. So, this value is 1. So, now theta eta you express in terms of other terms. So, you can write theta eta is equal to 1 minus theta prime 0 eta to infinity e to the power minus 0 to eta Prandtl number by 2 f d eta d eta. Okay. So, now we are left with another boundary condition at eta is equal to 0, theta is equal to 0. So, now let us put that boundary condition. So, another boundary condition is there at eta is equal to 0, theta is equal to 0. So, if you put that value, so left hand side you have 0, 1 minus theta prime 0, 0 to infinity, okay, eta is equal to 0. So, e to the power minus 0 to eta Prandtl number by 2 f d eta into d eta. Now, you can find the value of theta prime 0, right. So, theta prime 0 will be 1 by 0 to infinity e to the power minus 0 to eta Prandtl number by 2 f d eta d eta. Okay. So, once theta prime 0 is known, so now you can find theta eta. So, theta eta you can write 1 minus, in the numerator you have eta to infinity e to the power minus 0 to eta Prandtl number by 2 f d eta divided by 0 to infinity e to the power minus 0 to eta Prandtl number by 2 f d eta d eta. Okay. So, this is the temperature distribution. So, if you know the function f, then you will be able to integrate and you will be able to find the temperature distribution using some numerical technique. You can solve this equation. So, in this equation now you can see that if you write theta eta, so it will be 0 to infinity e to the power minus 0 to eta Prandtl number by 2 f d eta d eta. So, it will be 0 to infinity e to the power minus 0 to eta Prandtl number by 2 f d eta d eta minus eta to infinity e to the power minus 0 to eta Prandtl number by 2 f d eta. Okay. So, you can see another d eta will be here, another d eta will be here. So, now you can see this integrand is same in both the integral, but the limits are different, 0 to infinity and eta to infinity. So, if you subtract that, so obviously you can get 0 to eta. So, theta eta you can write 0 to infinity e to the power minus 0 to eta Prandtl number by 2 f d eta d eta, and this we are writing now 0 to eta, 0 to infinity and it is eta to infinity. So, you are subtracting. So, you will get the limit 0 to eta e to the power minus 0 to eta Prandtl number by 2 f d eta d eta. So, this expression also we can write in terms of f double prime. So, we will start with the Blasius equation. So, whatever we have derived in last class. So, you can see Blasius equation, that is your f triple prime plus f by 2 f double prime is equal to 0. So, you can write d of d eta f double prime divided by f double prime is equal to minus f by 2. So, integrate this equation. So, you will get 0 to eta d f double prime by f double prime is equal to minus 0 to eta f by 2 d eta. Okay. So, now you can see that you will get ln f double prime, which is function of eta divided by f double prime at eta is equal to 0 is equal to minus 0 to eta f by 2 d eta. Now, multiply both sides with Prandtl number, multiply both side with Prandtl number. Okay. So, if you see here, if you multiply Prandtl number, so you can write this as ln f double prime to the power Prandtl number divided by f double prime 0 to the power Prandtl number, and here you can see minus 0 to eta Prandtl number by 2 f d eta. Okay. So, from here you can write f double prime to the power Prandtl number divided by f double prime 0 to the power Prandtl number is equal to, so it will be exponential, right, e to the power minus 0 to eta Prandtl number by 2 f d eta. So, if you see in the last expression, whatever you have e to the power minus 0 to eta Prandtl number by 2 f d eta. So, that expression we have written in terms of f double prime. Okay. So, f double prime 0 you know, right, because f double prime 0 we have found from the velocity distribution. So, this is the velocity gradient at eta is equal to 0 and that value is 0.33206. Okay. So, now if you put this in this expression, so what you will get? You will get, so the dimensionless temperature, distribution you will get theta, which is function of eta as well as Prandtl number, is equal to 0 to eta f double prime to the power Prandtl number d eta divided by 0 to infinity f double prime Prandtl number d eta. So, you can see here in this expression. So, obviously f double prime 0 to the power Prandtl number is there, and so whatever expression we have got here e to the power minus 0 to eta Prandtl number by 2 f d eta. So, that expression you put in the expression here, okay, in this expression, and you just rearrange it. Finally, you can write the temperature distribution as the dimensionless temperature distribution. Okay. So, after rearrangement you will get theta, which is function of eta and Prandtl number, is equal to 0 to eta f double prime to the power Prandtl number d eta divided by 0 to infinity f double prime Prandtl number d eta. Okay. So, after doing some rearrangement you will get this as the final temperature distribution, and you can see, if you know the value of f double prime from the velocity distribution, you will be able to calculate the temperature distribution. So, this equation you can solve numerically. So, now let us see that as a special case, whatever we started with, that for Prandtl number 1, what is the temperature distribution? Okay. Is it same as the velocity distribution? Let us see. So, for Prandtl number 1, okay, this is a special case. So, for Prandtl number 1 you can see what you can write, theta eta for Prandtl number 1 is equal to 0 to eta. Okay. So, Prandtl number 1. Okay. So, you can write d of f prime, okay, d of d eta. So, d eta will get cancelled. So, d of f prime, and in the denominator you have 0 to infinity d of f prime. Okay. So, now you can see it will be, if you put the limit, so it will become, so f prime eta minus f prime 0 divided by f prime infinity minus f prime 0. Okay. So, now what is f prime? F prime is the velocity u by u infinity, and at eta is equal to 0, f prime is 0. So, you can see this is your 0 and this is also 0. And what is f prime at eta tends to infinity? So, that is your 1, because u tends to u infinity. So, this is your 1. So, you can see that from this expression that theta eta is equal to f prime eta, and what is f prime? It is nothing but u by u infinity. Okay. So, the dimensionless temperature and velocity distribution are identical for Prandtl number is equal to 1. That means, for Prandtl number is equal to 1, okay, you have delta is equal to delta t. So, it will be the non-dimensional temperature distribution will be same as non-dimensional velocity distribution. So, in today's class we have started with the energy equation, and we defined on non-dimensional temperature theta as T minus T w divided by T infinity minus T w. We have assumed in the beginning that T w is function of x, and we have derived the Paul-Housen equation in general, which is your second order linear ordinary differential equation, and we have shown that using similarity variable approach we could convert the PD to OD for any Prandtl number. For special case lambda is equal to 0, the wall temperature becomes constant, and for that we have found the solution for temperature distribution, and this temperature distribution we have expressed in terms of your velocity gradient f double prime. Once you know the velocity distribution from the solution of Blasius equation, you will be able to find the temperature distribution. So, you can solve this equation using some numerical technique, and at last we have shown that for Prandtl number is equal to 1, the temperature distribution and velocity distribution are identical, and you can write that theta is equal to u by u infinity. Thank you.